Welcome back. Now we are looking at section 6.2 volumes. These volumes are created by taking a function and rotating it around some axis. So before we do that, let's talk about what we're going to use. I want to talk about volume, and I'm going to look, instead of using strips, when we rotate these strips, we're going to create cylinders or disks. In this case, we're using disks. So I say I want to find the area of these cylinders. And the area is equal to the base times the height. So the area of a circle, right, because what we have here is this area of the circle, and it's multiplied times its height. So the area of the circle is pi r squared times its height. Here's a nice little illustration. We're going to turn this on its side. If we look, we had some function that maybe started off here, came through here, like this. This would be its strip. And when it rotated this around this axis y equals x, it created the cylinder. Now we're going to look at the cylinder and we're going to say, I'm going to find the volume of the cylinder is pi r squared times h. Well, the function is my r, or is the height here. And I'm going to have a delta x because I'm going to take this width and get it incrementally small until it's almost nothing. And so it's going to be flat disks that we're going to pile on top of each other. So they're going to look something like this. We say the volume is equal to the summation of pi times the function f of x squared times delta x. And we do that, and we learn in Calc 1 that this is through the Riemann sums, that we can integrate this from a to b now. And it's going to be pi times the function f of x squared dx. And each one of these is what we're going to evaluate. Here's a nice little drawing. It says, look at this function called y equals f of x. I want to know the region. I'm going to rotate it around this axis. I'm going to rotate it around the x-axis. I'm going to get this funky looking thing here. I'm going to look at a particular slice, my delta h, because we're going to make those incredibly narrow. My strips are always going to be drawn perpendicular to what I'm rotating when I'm using what's called disks. We're going to learn about shells in the next section, and that we're going to do slightly differently. You need to know how to do both of these. So when I look at this, I have a volume here. This is a slice from that volume, and there it is. Now, sometimes we have white space. So I don't want this white space here. So I have these two functions. I want the area between the two. Y equals f of x, y equals g of x. Top function, subtract the bottom function. So my big R squared, which is my top function, subtract my little r squared, times my h. And these are called disks. These are called washers because there's a hole in there. So we have pi times big R squared minus little r squared. And we're going to define what big R squared is and little r squared as we're going along. I'm going to integrate from a to b. Always have a pi. Larger function, subtract the smaller function, because again, I want this white space removed. That's why we had to learn about how to find the area between two curves, because these two curves are being rotated around, giving us this hole in here. So here's the function. This is a link that you can copy over. I'd show it to you, but this computer doesn't have the latest flash. If you go to this link, there's a couple of little volume movies or MP4s that you can look at, and you can see how volume works. I think they're really neat to look at. So to save some time, I went through my notes and I already drew out all the functions, so we don't have to watch me draw them out. But we're going to do all the work still. So here's the first one. It says, find the volume of the solid obtained by rotating the region bounded by the given curve about the specified line. Sketch the region, the solid, and the typical disk or washer. This is not going to be a washer because it's going to be a total solid there. So y is equal to square root of x minus 1. That's this function here. I'm going to go from x equals 2 to x equals 5. It's bounded below by the function y equals 1. So we're looking at just this area here. Whoops. Okay, just this area here. and we're going to rotate it. It says around the x-axis, so I'm going to draw a little line here to remind myself what I'm rotating around. Actually, let's do a different color. We'll pick blue. I'm going to change my line thickness real quick. And so, or green. I had green already. We're going to rotate around that axis there. Now, when we rotate around that axis, that means the function is going to do this. We'll also get a bit that comes down through here. And we're going to have this area also. We're going to create a disk. Now, I told you when we're working with these, the first thing we should do is draw on our strips so we know what we're integrating it with respect to. Our disks are always going to be drawn perpendicular to what we're rotating. So that gives me a delta x. I know my x's are ranging from from 2 to 5. I need a pi. My function, f of x, is equal to square root of x minus 1. So I have square root of x minus 1 squared dx. I'm going to square it. Squaring a square root just gives me x minus 1 dx. I will then integrate x squared over 2 minus x from 2 to 5. I'm going to substitute my values as I integrate it, as I evaluate it, that is. 5 squared over 2 minus 5, subtract 2 squared over 2 minus 2. When I'm done calculating it, I should get 15 pi over 2. 15 pi over 2. So that was a very simple one. We were just rotating around the x-axis. We didn't have to change our limits of integrations. We were told it's going from 2 to 5. Our strips gave us a delta x, so everything worked out fine. So now in this one, it says find the volume of the solid obtained by rotating the region bounded by y equals x cubed. That's the function in red. And y equals 8, which is the function in blue. And x equals 0. So we're looking at just this area here. Again, I'm going to take my time and I'm going to draw in what I want to have my function. I'm going around the y-axis, which is this axis. My strips need to be perpendicular. So that gives me a delta y. So I'm starting off with y is equal to x cubed. Well, I need to have x equal something. So I'm going to take the cube root of both sides. I get x is equal to the cube root of y, or y to the 1/3. So now I have my function. My my function, f of y, is equal to y to the 1/3. I'm evaluating. My y's go from 0 to 8. So I'm going to integrate from 0 to 8. I still need the pi on the outside. The function I'm evaluating is 1 over y to the 1/3. I need to square it. And I'm doing that with respect to y. Next, I'm going to square that. Y to the 2/3 dy. After I've done that, I'm going to integrate. I'm going to add 1 to that, so I get 5/3. I got to remember to have a 3/5 in front. I'm going to go from 0 to 8. Remember, because I have to be able to go back to what I originally was. That's why I need the 3/5. So then I have 3 pi over 5 times 8 to the 5/3. Subtract 0 to the 5/3. Well, 8 to the 5/3. The cube root of 8 is 2. So I really have 3 pi over 5 times 2 to the 5th, subtract 0. or I have 3 pi over 5 times 32, which gives me 96 pi over 5. If you want, you should probably pause these and do some of the work on your own and make sure you're getting the exact same answers that I am getting. On your test, these are problems I would expect you to be able to do without a calculator, and you would be able to find these functions. Now, there's some functions that are just too difficult for you to know how to find or find their intersections, and we would have a calculator for that. Now we moved on to the next problem. It says, find the volume of the solid obtained by rotating the given region bounded by the given curves about the specified lines. Sketch the region, solid, and the typical disk or washer. So I have two functions, y equals x squared. I have y equals 4. I know that I'm going to go from 0 to 2. So again, the area that I'm concerned with is just this. It's telling me I want to go about the y-axis, so that means I'm going to rotate around that axis. Here are my strips. Again, I'm going to draw my strips in. This is a good habit to get into, because then I can't mess up that it's delta y's over delta x's, or I can make sure that the strips actually make sense, that I'm not running into myself. This will make a lot more sense when we get to the other type of finding volume, which is shells. It's delta y, so my y's are going to range from 0 to 4. So I'm going to go from 0 to 4. I have y equals x squared. Well, that doesn't help me. So I have y equals x squared, or x is equal to y to the 1/2. So my function I want to evaluate, don't forget my pi out front, it's y to the 1/2. I need to square it. I'm evaluating in terms of y. So I have pi to 0/4 y dy. I'm going to integrate. From 0 to 4. That turns out to be 8 pi. These functions have been pretty simple. So now let's look onto the next slide. This is going to determine the volume using disks. Strips are drawn perpendicular to the x-axis you are rotating around. That's why I said you should continue to draw in your strips so that you make sure you're doing it correct, that you're integrating with respect to the correct value. Volume is equal to the integration of pi times the radius squared with delta thickness. So now we're going to look at something different. We've looked at the discs, but we haven't done anything with washers, the white space. Remember, I drew that there was that one picture that looked like this, and had all this colored in, and we wanted to get rid of that white space in the middle. So this is my function. This would be the f of x. This function here would be my g of x. And then I would take the function f of x as it rotates around, and the function of g of x as it rotates around. So it does something like this. It gives me this area and this area. Sorry, the drawing's not so pretty. When I rotate it around, it creates a solid, but there's also some white space. So we have to say, all right, well, I'm going to look at integrations of pi from a to b of f of x squared, my outer function, dx, minus pi from a to b, the same a to b, of g of x squared, my inner function. I will call it big R for the outer function and little r. Why am I calling that? Because the radius from here to here is big R squared, and the radius from here to here is little r squared. Right? Because that's going to allow me from here to here. Let's change the color here. From the center out here is big R squared. From here to here is little r, which we're going to square again. That way I can remove the little r squared would allow me to remove the area, give me the white space. Instead of integrating two things, we'll just say it's pi times the function of f of x squared subtract g of x squared. Now, if we did the same thing about the y-axis, we're going to get the exact same formulas, except for in terms of y instead of in terms of x. So no need to going over the example of drawing it out for you. So now let's look at this. It says, I want the region R enclosed by the curves y equals x, which I have drawn in blue, and y equals x squared, which I have drawn in green, rotated about the x-axis. So here's my x-axis. My strips, again, are always perpendicular. But now I have white space. So I want just this area. But when I rotate it, I get all this other area I don't care about, which is in yellow. The yellow function is what I need to subtract out. So here we go. I want to integrate from a to b of my big R squared minus my little r squared dx. So let's define everything. R squared, big R squared, is equal to x. Well, let's start over. Big R is equal to the function y equals x. Because it's the outside of that. When we rotate it around, right, this is still y equals x. So then I need big R squared, gives me x squared. My inner radius is bounded by the function y equals x squared. So little r is equal to x squared. Little r squared is equal to x to the fourth. Now, some things I haven't found. I still need to know where they intersect. I know they both intersect at 0, but again, to find their intersections, we set them equal to each other. I go x squared is equal to x squared minus x equals 0, x times x minus 1 equals 0. They intersect at 0 and 1. This is a skill we need to be able to use. So if they intersect at 0 and 1, here's 0, here's 1. Those are my x values. So I know I'm going to integrate because my x's are going to range from 0 to 1. Still need a pi. We said that big R squared was x squared. Subtract little r squared, which we said was x to the fourth. We calculated that up here. And that's going to be in terms of dx. I'm going to integrate. I get x cubed over 3 minus x to the fifth over 5. I'm going to go from 0 to 1. I get pi times 1/3, subtract 1/5, subtract 0, because 0 goes in for x, and that all turns out to be 0. And then it turns out my final answer is 2 pi over 15. That's that volume with us removing all this yellow. We removed all this yellow, but we kept all this blue. And we rotated around the x-axis. So now here's another one. I want to find the area bounded by the function y equals x squared plus 1, which I have in blue, and the function y equals 2. But this time I want to rotate around the line y equals -4. So I still want this area here. There's going to be some, when I rotate it around, there'll be some line over here. I'm going to just draw an imaginary line here. Obviously, this isn't to scale. This is what I'm rotating around. So there's a lot of white space. I'm going to draw my strips because I'm going to always draw my strips perpendicular to what I'm going to rotate around. There it is. That gives me delta x's. So I know I want everything in terms of x. Here's something that we haven't done. I know I have my larger disk, right? This is my outside perimeter. This is my inside perimeter. So my big R is equal to 2. But the problem is I'm rotating from here to here. So it's not just 2, it's 2 subtract -4, which is 6. All right? Because the distance, right? I have to talk about that distance. That R is going to go from here to here. Before we were using 0, it was either x equals 0 or y equals 0. So we didn't talk about subtracting it. But remember, my strips, the bottom of my strip, top of my strip, I need to have the length of my strip. So in this case, my length of my strip is going to go from -4 to 2. So you take the larger number, 2, subtract the smaller number, in this case it's -4, give me 6, or I get big R squared is equal to 36. So little r is the function x squared plus 1. But again, I have to have, I'm looking at trying to get rid of something. So my little r, give me a second here. This strip is what I want to remove. So the distance from there is going to be x squared plus 1 subtract that -4. So when I do that, I go through, r is equal to x squared negative plus 5. So r squared is going to be x squared plus 5 squared, or x to the fourth plus 10x squared plus 25. So now we have what we were looking for. Remember, when we're integrating, this is a washer, a to b, pi, big R squared, subtract my little r squared, and this is going to be in terms of x. So I have pi. We said we're ranging, right? Our x's are going from 0 to, oh, we didn't find it, did we? I guess we need to find that. Hopefully you figured it out. It should go from 0 to 1. And I'm going to double it. It actually goes from -1 to 1, but I'm going to double it. Again, remember, symmetry, right? I could have gone from -1 to 1, or I could just go from 0 to 1 and double it. So I'm going to use the fact that I have symmetry. I'm going to say 2 pi. My outer, my big R, we claimed was 36. Subtract from it my little r, which is x to the fourth plus 10x squared plus 25 dx. So I have 2 to pi. So everyone, by the way, I could have just done pi from -1 to 1, r squared minus little r squared dx. I choose to double it. So now I have 36, subtract x to the fourth, subtract 10x squared, subtract 25 dx, combine whatever I can. So I have 2 pi from 0 to 1 minus x to the fourth minus 10x squared plus 11 dx. When I evaluate this, I get 2 pi minus x to the fifth over 5, right? That's what happens when we integrate, minus x cubed, 10 thirds, plus 11x. And I'm going to evaluate that from 0 to 1. I get 2 pi. When I put I put 1 in, I get -1/5 minus 10 thirds plus 11. And when I put 0 in for everything, I get just 0. I evaluate all that. I put it in my calculator if I have a calculator. If not, I do it by hand. I get 224 over 15 pi. 224 over 15 pi. Just rewrite this so it's 224 over 15 pi. And that's how we're going to do this. almost done. We have 3 or 4 more to do. So now, that's the problem that you'd see in your homework. It's saying, look, I want to refer to the figure below and find the volume generated by rotating the given region about the specified line. I want R2, so I need to find R2. Here's region 2. About the line OA. This is the line OA. I'm going to draw my strips. Remember, all the time my strips are perpendicular. So I want delta x's. So that's fine because all my functions are referred to as in that way. So I can see my limits of integrations are 0 and 1 for my x's. So 0 to 1. Don't forget my pi. Now here, my top function is the line y is equal to 1. 1 squared. My bottom function, because remember it's big R squared minus little r squared, dx ab pi. My little r squared is y equals square root of x, or x to the 1/2 squared dx. And I get pi from 0 to 1, 1 minus x dx. I'll give you a second to do all this work. Pause the video, and you should get the final answer of pi over 2. Let's look at the next one. This is again region 2. So it's the same region we were just in, but we're changing the line to BC. So this time our strips are going from here to here. There's still delta x. There's still delta x. So big R squared and little r squared. So I looked at this from 0 to 1. And I'm going to take, it's actually one function. So my strip is top. There's no big R squared. I just have R squared. It's top, subtract bottom. My top here is 1. My bottom here is square root of x. Right? Top of my strip, bottom of my strip. It's defined from there to there. From 1, subtract square root of x. I still have to square it. So r is just 1 subtract square root of x. Top of my strip, subtract the bottom of my strip. Again, this is in terms of dx. Don't forget the pi on the outside. When I square it, I end up with 1 minus 2 square root of x plus x dx. Now I'm going to integrate that. I get x minus, remember, this is the same thing as 2 to the x to the 1/2. So I'm going to add 1 to that, x to the 3/2. And I need 4/3 because when I evaluate this, I still want that to be a 2 out front as my coefficient. Plus x squared over 2. And I'm going to go from 0 to 1. I will then substitute 1 in, substitute the 0 in, and then I should get pi over 6. Give yourself a second to catch up. Hopefully, as I said, hopefully you can do this on your own, and you should get the answer pi over 6. I have one more for us to look at. Now again, we're looking at R2. We keep looking at the same region, but that's fine because this time we're going to rotate and have a washer. Because now we want to rotate around the line AB. So my strips are going this way. That's a delta Y. So you have to pay attention. Big R squared is equal to 1 minus 0, right? Right subtract left. It'll be right subtract left. My right-hand side is 1, and my left-hand side is 0. So it's right subtract x, right subtract left. and I'm going to square that and get 1. My little r squared, again, right subtract left, 1. But I have to remember that it's y is equal to square root of x. I don't want that. I want x equals, right? Because these are delta y, so I want x equals. So I get y squared is equal to x. So I get 1 subtract y squared squared, or 1 minus 2y squared plus y to the 4th. And remember, we're changing this. Again, it's 1, because x equals 1. That's the function there. X equals 0. That was my big R. Then I had my little r. Again, it's still x equals 1, but then I had this function here, which is what I want to remove. This is all the white space. I'm trying to get rid of all that white space. That's bounded by that function y equals square root of x. My y's are ranging from 0 to 1. So I'm going to pi 0 to 1. My big R squared, which was 1, subtract my little r squared, right? It's big R squared, subtract little r squared. 1 minus 2y squared plus y to the 4th dy. I drop my parentheses. 0 to 1. And I end up with 2y squared minus y to the 4th dy. I can evaluate that integral. I get pi times 2/3 y cubed minus 1/5 y to the 5th from 0 to 1. Again, I'll give you a second to work this out, and then I will show you the answer. So when I put in the 1, I get 2/3 minus 1/5. Put 0 in, everything turns to 0. And when I'm done, I get 7 pi over 15. That is the end of this section. I will tell you right now that section 6.2 and section 6.3, which is the next section I'm going to cover, tend to really make students struggle. You really need to work out some of these problems. I would go back, honestly, and look at the videos and work these out yourself. And then make sure you're understanding how to create white space, what's happening when I'm rotating around something other than the x or the y axis. Remember, we had to subtract top from bottom, right from left, right? Larger from the smaller value. We're always drawing our strips perpendicular to what we are rotating around. And I would play around with these and make sure you understand, how do I find my limits of integration by setting my equations equal to each other? How do I define those strips? How do I define what's big R and what's little r? You have to be able to do this. I'm going to tell you right now, a lot of students will struggle with this chapter test and not do well. It's a hard concept for some to understand. All right, good luck, and I look forward to seeing you in the class.